In this video, we're going to be taking a look at a charged particle that enters an electric field, and then we're going to see how far it can travel before it comes to rest. Now, we have an electric field going from left to right, and we have an electron that is moving to the right with an initial velocity of 1.7 times 10 to the 6th meters per second. And electric field lines are the lines that show us the direction that a positive test charge would go. So because this is negative, it's going to feel the opposite effects. So the electric field is going to be pushing against the electron, causing it to slow down. So what we're going to do is figure out how far can this little electron make it into this electric field. Now, we're basically trying to figure out how much energy this electron has and basically what the electric field has to do to remove all the energy from the electron to bring it to rest. So if we know that the electron has some kind of velocity, then we can safely assume that it has some kinetic energy, and kinetic energy is 1/2 mass times velocity squared. And what we're going to do from there is, if we know that it has kinetic energy that is eventually going to come to zero at some point, then we know that work is being done. It is negative work. It's work being removed from the electron. So eventually, this value of kinetic energy is then going to be translated into work, and work is force times distance. Now, the final thing we are looking for is the distance. How far is it going to penetrate into the electric field? So what we need to do then is also solve for the force. So we're going to need one more equation, and then we can go ahead and use this formula where the force equals the charge times the electric field. Now, using a combination of those three formulas and a little bit of algebra, then we can go ahead and solve for our final distance. So let's go ahead and plug in those numbers and solve for that distance. All right, so what I did was I found the kinetic energy of the electron initially, which is 1/2 m. This m is a constant, which is the mass of an electron, 9.1 times 10 to the negative 31st kilograms. So that's where I got that variable from. The velocity was given in the problem, so I took the 1.7 times 10 to the 6th meters per second and made sure I squared that. That gave me an energy of 1.31 times 10 to the negative 18th joules. Secondly, I solved for the force. I also took a known value, which is the charge of an electron, negative 1.6 times 10 to the negative 19th coulombs, and then multiplied it by our electric field of 6,100 newtons per coulomb. When I multiplied those, I got 9.76 times 10 to the negative 16th newtons, and that is actually negative because we have one negative multiplied by a positive, and that negative force means that the force is pushing in the opposite direction, which makes sense because it's pushing against the electron to slow it down and bring it to rest anyways. Now, for our final calculation, if you notice, I took this number, but I placed a negative in front of it because the amount of energy that was transferred was negative because you're taking out 1.31 times 10 negative 18th joules. It is a negative delta K change in kinetic energy for the work. So we have negative 1.31 times 10 to the negative 18th joules. And then we divide both sides by the negative 9.76 times 10 to the negative 16th newtons. And then we get our final distance of 0.0013. So I hope that was helpful in helping you solve for the amount of distance an electron can travel into a particular electric field. Thank you for watching and listening.